Okay, so the first one is really just chain rule, and you can just steal all your numbers actually right from the table. So I usually write it out first, then I put in the sixes, then I look at the table. I don't usually start by looking at the table, but that's just me. Anyway, you end up with 1 times 3. And then you're adding negative 2 times 2. So you get that one. 2, you're going to use probably quotient rule. So remember, it's low, D high. Don't get that backwards, right? Low, D high is first. And then you can plug in, this time we're doing h prime of 2. So plug in the 2. Plug in all the numbers. For that one I got negative 7/6 after all is said and done. You can double check that real quick. Anyone else get that? You have to plug in g of 2 times f prime of 2. So that's negative 3. Then you have to do f of 2 times g prime of 2, which is basically 5 times 3 halves. 5 times 3 halves is 15 halves. You just write 15 halves. And then this is all over g of 2 squared, basically 9. And then usually I'll just multiply top and bottom by 2 for something like this. So you get 18 on the bottom, but up top you get negative 21. So that reduces to negative 7/6. Okay, let's look at parts 3 and 4. Okay, so this is like a chain rule sort of thing. So can you help me with the derivative of this one, Lauren? We have f of x, and it's squared, and we're ddxing it. So what is the procedure here?
So we bring like 2 to the front, and then so 2 f of x, and then multiply by f, and then, or f prime of x.
Right. And then maybe save plugging in the 1 for later, right? Okay. And then you could just steal all the stuff from the table. So f of 1 is 6 actually. And f prime of 1 is negative 1. So negative 12. That's a 6. Okay. Number 4. Now we have f with g plugged in. And we're doing the derivative. So this is sort of an inner function, outer function sort of thing. We do outer function first. So you want to help me with that one, Francie?
Can you do the f prime of g of x
Right.
times g prime of x?
Yeah. And then just check we're doing at 1. So just plug in 1. F prime at g of 1 times g prime at 1. So here you're going to have to find what g of 1 is. G of 1 is 2. G prime of 1 is 1. So f prime of 2, you have to find that now. That's like the last thing to find. So it's negative 1 times 1. For the last one I got negative 1. Negative 1 is my final answer. Okay, pretty straightforward, right? Okay, inverses. I'm not too fond of this particular example. Okay, so I think I'm going to switch the example a little bit. Partly the reason I don't like this example too much is because this isn't really a one-to-one function, so it doesn't have an inverse function, although it does have an inverse relation. So I'm just going to switch this up. I'm going to give you another function. Question?
Wait, what do you mean by one again? Or what do you-
Oh, it just means it doesn't, this is a parabola, so it doesn't really pass the horizontal line test. You know what I mean? It's some kind of left-shifted parabola or something. So because it doesn't pass the horizontal line test, it has an inverse, but the inverse is not a function. So when you take the derivative, you actually get two answers on this. So I didn't really want to do an example like that, mainly because I've never seen one on the AP test. But what I want to do is switch this and go ahead and make this the cube root of x minus 5. I meant to do the fifth root. X minus 5 cubed plus 1. And I would like to find, actually hold on, let me start this part again. Yeah. So we're going to solve this problem, and G is the inverse of F, but we're going to find G prime of 2, not G prime of negative 4. Okay, so find the derivative at x equals 2. The derivative of the inverse. So it's kind of a hard problem in a way. So there's so many ways to do it, but here's the basic theory behind the problem, okay? So the idea is this. You want to study a graph called G. G is the inverse function of F. So whatever you want to learn about G can be learned from F, all right? So if you have a function like this, F, right, and it contains a point A, B, then the inverse function, which is really just a reflected function is all it is, the inverse function will contain what point? It won't contain AB necessarily. It'll contain what? BA, correct? And its name, of course, is F inverse. And the slope on the first curve and the slope on the partner point on the second curve clearly are not the same slope. Right? Why would you think these are the same? They're not the same slope. Yet they're not really perpendicular either, right? They're not parallel lines, they're not perpendicular lines. Can you kind of guess what is the relationship between the slopes of these two tangent lines? What do you guys think the relationship is? What do you mean by inverses? Okay. Yeah, the idea is x and y are all trading roles, right? When you hop over the line. So if that's the case, then delta y over delta x is going to change over to become delta x over delta y. See? So if this slope is 2/3, this slope is 3/2. Does that make sense? If this is 4/5, then this slope is 5/4. That's not an opposite reciprocal relationship. It's just a reciprocal relationship. So what you can say is, this is a true statement right here. Ready? F inverse's derivative at 5 is the same, not 5, I don't know where I got 5 from. At B is the same thing as the reciprocal of F's derivative at A. So F inverse's derivative at B is the same as the reciprocal of F's derivative at A. So that's kind of confusing, but that seems to be what we're looking at here, right? So the hardest part of this problem is figuring out A and B. Okay? But that's the rule. Let's go ahead now and see if we can figure out what B is. We want to find basically F inverse's derivative at 2. That's the question. But we're going to have to do this by finding the reciprocal of F's derivative at some other number. Okay? So this is kind of the hard part. So what you don't want to do is plug in 2. You do not want to plug in 2 into this function. It's not going to work. Okay? 2 is an x-coordinate. Okay? It is an x-coordinate, but not for F. It's one of F inverse's x-coordinates. That 2 is not an x-coordinate of F. It is F an x-coordinate of g. So how would you understand the two then in terms of function f? It's not an x-coordinate. What's that?
Would you work out?
No?
Would you find,
What were you going to say?
would you find the y coordinate of 2 at,
You're definitely doing the right thing. So you said we're going to make y2?
yeah, and then you find the x.
Correct. So we need to figure out what x-coordinate on the f function yields to. See? So we're going to actually set this side equal to 2 and see if we can figure out what x is. After we know what x is, we'll know what to plug into f prime. Okay? It's kind of awkward. But you need to set 2 equal to the 5th root of x minus 5 cubed plus 31. Go ahead and solve that real quick. Once you know what x is, we'll know exactly what points we're dealing with. What did you find? Anyone else get x equals 6? That's correct. So if you do a 5th power on both sides, you get 32 equals x minus 5 cubed plus 31. Subtracting the 31, you get this. And you don't have to go any further. X is 6, folks. Look at it. Right? Okay, so x is definitely 6. What does this mean? This means that f, the function f, passes through the point 6, 2. See? And the function g passes through the point, of course, 2, 6. See, they're inverses. So we are able to find g prime at 2 only because we know f. We're going to go back now to f. We're going to find its derivative, but we're going to plug in 6. It will give us the reciprocal of the derivative of the inverse at 2. It's kind of confusing. So let's go ahead and find f prime of 6. We'll flip it over, and that will give us the same thing as f inverse prime at 2. If that makes sense. All right, so go ahead and do that. Now you have to find the derivative of f. Okay, so remember f can be written this way, right? X minus 5 cubed plus 31 all to the 1/5. So what is the derivative? 1/5, right? X minus 5 cubed plus 31 all to the negative 4/5 times the derivative of the inside, which fortunately is just 3x squared. No, 3 times x minus 5 squared, excuse me. 3 times x minus 5 squared. So before you panic, you're plugging in 6, okay? So 6 is actually a pretty friendly number here. So you have 1, you're going to plug in 6. It's supposed to have a little bar, and then x equals 6 down there. So you're going to plug in 6, so you're going to get 1/5. Erase my graph now, so we know what we're doing. 1/5. This is just going to be 32 to the negative 4/5 times, and then this is just 3 times 1 squared. So you end up with a 3 on top, a 5 on the bottom, and a 32 to the 4/5 on the bottom. You do not need a calculator. The 1/5 power of 32 is 2, and 2 to the 4th is 16. So it's really just 3 over 5 times 16. In other words, 3/90ths, or 1/30. So this is just 1/30, if I'm not mistaken.
Mr. Shore, how did you do the 32 to the 4/5 power?
Well, you mean here? I'm plugging in 6 for
No,
x.
no, no, I'm
right?
sorry, how did you, like, you just reasoned out the 32 to the 4/5 power? What did you say?
This goes to the bottom. It's 32 to the 4/5 goes to the bottom. Oh, the 1/5 power is 2. It means 5th root of.
Okay.
So 32 to the 1/5 is dos.
Mm.
2 to the 4th is 16. 5 times 16 is, it's 80, isn't it? I'm sorry, it's 3/80ths. 5 times 16. 5 times 16 is 80, not 90, sorry. So yeah, it's 3/80 is the correct answer here. 3/80. And so our answer is 80/3. Be careful, we were going to flip that, remember? Okay, there is one other way to do this. And what you have to do is first find the inverse function, then take its derivative. Or there's a third way. You could find use implicit differentiation to find the inverse's derivative. I don't think it's any easier, to be honest. At some point, you're going to have to figure out that the point 6,2 is on the graph of f, and 2,6 is on the graph of g. There's no way around that. So, yes.
How do you do like inverses? Like when you give like a chart? Is there a way on the test?
Okay, that is actually a lot easier. Let me show you how we can do that on. This was our chapter 3 test, and there were there's a table at the top of the page, and numbers 7 and 8 and 9 and 10 were all referring to this table, okay? When you get to number 10, that one's sort of the hardest one. Okay, the reason this particular problem is harder than the other three is because there was no table for the function p. But we can fix that. So first of all, p is just f inverse, right? So we probably don't need g at all, right? Forget g. What you need is f's table, and we're just going to do an inverse table. So watch how we can make an inverse table pretty easily. The points in the table will be 1/2, 1, 1, 2, 3, 3, 4, 4. Can someone tell me how I got that table filled in so quickly? What did I just do? All I did was switch what? X and Y, right? These are 4 points on the function p, you have to admit. Now I'm going to make a p prime column. Ready? 1, 2, 1/2, 1/4. How did I make that so fast? So quickly? What did I do to my f prime column? So what did I do? I just did the 4 reciprocals. Reciprocal of 1, reciprocal of 1/2, reciprocal of 2, reciprocal of 4. So what you're looking at here is a table for p, which is the inverse of f. It has all the opposite x's and y's, and it has all the reciprocal slopes. Now the problem's easy. What's p prime of 1? You've got a table. P prime of 1. Let's find it in the table. What's the answer? 2. Right. I could ask you now, what's p prime of 1 plus p prime of, 3? That would be a really hard problem if it weren't for the table. But here, p prime of 1 plus p prime of 3 would be 2 and 8. Easy. So how did I make the table? I just switched the 2 columns and reciprocal all my slopes, reciprocated. I wish we had had a table on that other problem we did a minute ago, I guess we could have made one. Make a table for f, create a table for f inverse, I'm not sure it would be as easy though. Okay, so inverses are just hard to work with. So you definitely need to practice that. And you can find more problems online, or I have a whole worksheet of those if you want sometime to borrow that. Okay? I actually have a workbook, and it has topic by topic different things. So whenever you find a weakness, come back to me, and I'll help you by giving you a worksheet that will help you with that specific topic. Okay, so page 2's optimization. This is a lot of verbiage here. Let me boil it down to 3 simple things for you, okay? Number 1, write an equation. Number 2, get it in one variable. Number 3, find the extrema. So, find the extrema. It really is a simple 3-stage problem mentally. The reason there's so much verbiage here is because they're trying to tell you what equation you'll create, and how you're going to make it into one variable. But after you see an example, you're like, I didn't need to know all that. Just give me the 3 basic steps, So obviously, the equation you're going to write is that of the object you're trying to optimize. So, for example, if it says, what is the cheapest cost? You'll try to write a cost equation. What is the minimum surface area? You'll try to write a surface area equation. What is the maximum volume? Write a volume equation, you see. This first problem is a great one, and it teaches us everything we need to know about optimization. When you're done with this problem, parts A and B, there's nothing left to study, except maybe practice it some more with different ideas. We have a piece of wire. It's 40 centimeters long, so everybody draw a piece of wire. Let's pretend that's 40 centimeters. This is going to be cut into 2 pieces. Does it say 2 congruent pieces? No. So, evidently it's going to be cut into 2 random pieces, maybe x and 40 minus x. Can you see why it's wiser to use x and 40 minus x rather than x and y? Why use 2 variables when you don't have to, right? Okay. So in Algebra 1 class, you did something like this. The string was x here and y here. And then you wrote down that x plus y is 40. Yeah, but that just means y is 40 minus x. So what a waste of time that was. So try to think in one variable as much as you can. Okay, what were we trying to do with this piece of wire? We're going to take one piece and bend it to form a circle. And we're going to take the other piece and bend it to form a square. I've done that before. 2 pipe cleaners or whatever, cut a pipe cleaner and make 2 shapes, whatever. So it's kind of up to you guys. Do you want to use the 40 minus x piece to make a circle? Or do you want to make a square out of that piece? I think it's wise to make the square using the 40 minus x piece. So here's the piece. We bend it into a square shape. How does the 40 minus x pertain to the shape of the square? What does the 40 minus x represent now? It is the perimeter of this square. Right. So the perimeter is clearly 40 minus x. My pre-calc students had a really hard time understanding that. Trying to explain to them that you just wrapped it into a square, so that's now the perimeter. And then I asked my Algebra 2 kids to find the side length. They had a little bit of trouble with that. Actually, these are pre-calc kids, sorry. They had to do what? Divide by 4. So it took them a while, but they finally figured out that this is 40 minus x divided by 4, and this is 40 minus x divided by 4. And in this problem, we are actually going to be trying to cause the sum of the area in the circle to be a minimum. So this question is really all about area. So maybe we should write down the area of our square. What is the area of the square? 40 minus x over 4 times what? 40 minus x over 4. So this is our area, correct? All right, let's look at the other piece of wire. We bent that thing into a circle. The x represents the what of the circle? Yeah, the x is the 2 pi r, right? The circumference is x. The circumference is x. I thought circumference was 2 pi r. Yes. Circumference is 2 pi r, and circumference is x. So this is really hard for my pre-calc kids. And then they need to write down the area formula, right? So the area is supposed to be pi r squared, but what's my radius? Yes. So this is really hard for my pre-calc kids, but this is actually kind of where I have them stop. They don't know what to do with these. I think I just had them add these two together and call it total area. But this is the area of our square. This is the area of our circle. And remember I said step one was to create an equation of that which you're trying to optimize? We are trying to minimize the sum of the area of the circle and the square. So our equation, and fortunately it's already in one variable, our equation is this plus that. So we just accomplished steps 1 and 2 of a 3-stage process. That's encouraging. Okay, so total area is what we wish to optimize. And the formula is 40 minus x over 4 is squared plus pi times x over 2 pi squared. There it is. Step 3 of optimization is to find the x that makes this max out or min out. You know, make it the extreme. So we would take the derivative, set it equal to 0, find the critical points, then we would try to plug in the critical points and the endpoints to see which creates the smallest solar area. So this is just like any other function now. You want to find the x that represents the peak, or in this case, the valley of the graph. Okay? So what pre-calc students do is they take this and they just plot it on the screen and they find the bottom point using the min finder on their TI-84. What you guys are supposed to do is take the derivative by hand, right? Set it equal to 0, find the critical points, and then you test both endpoints and critical points to see which makes the smallest area. Okay, so we'll pursue it a little bit, but let's go and find the derivative. A prime. You don't even have to expand it, right? You just take the derivative straight up. Just bring the 2 down. You have a 40 minus x over 4 to the first, and multiply by the derivative of the inside, which is negative 1/4. Then bring the 2 down, and then it's x over 2 pi to the first, and multiply by the derivative of the inside, which is 1 over 2 pi. Set this equal to 0 for optimization. And you have basically 80 minus, it's actually negative 80 plus x over 16. Negative 80 plus 2x over 16.
Shouldn't the derivative of the inside be 2 plus or 4 plus?
No, the derivative of the inside is negative 1/4. Negative 80 plus 2x over 16. And the other one, this 2 pi actually cancels. And you just basically get x over 2 pi. You try to solve for x. When you're done, you might want to make a little table or something to kind of organize your thoughts. Okay, so you're definitely going to be plugging in your critical value. Maybe we can solve this in the calculator real quick. So we learned that x is 8 pi.
Mr. Shannon,
Sorry, I recalculated 17.6. Thanks for catching that distribution error. Okay, 17.596 technically. So you're definitely going to be testing that value of x. So 17.596 is a candidate for a minimum. It's not necessarily a minimum. Now let's talk about the other meaningful values of x on this problem. Is it possible that maybe the minimum's total area could occur if we never cut the string? Right? In other words, what are some meaningful values that x could take on? So x must be a number between what and what? That's endpoint consideration. So what's the smallest x could ever be in this picture? 0. If we never cut the string. What's the biggest x could ever be in this picture? 40, right? Because x is a part of the string. So its meaningful real-life constraints are 0 and 40. Okay? 0 and 40. These are the 3 candidates for x. So I tested these earlier, and I determined that actually my areas were the following. Okay, I think I'm getting 56.0099 for that. This is when I plug in 17.596. And then if you plug in 0, I don't need a calculator for that. If I plug in 0, that's going to give me 1600 over 4, or just 100. And then this part is gone. So this is just 100. If you plug in 0, you get 100. And if you plug in 40, the first term vanishes. In other words, there is no square. Of course, you used it all for the circle. You used all the wire for the circle. So you just end up getting 20. Basically, you're going to have to calculate. If you plug in 40, you're going to get 1600. Let me just do it on the calculator. What's pi times, and then 40 over 2 pi, 20 squared. It's just 127. Okay, 127.32395, or 127.324. Okay, so you can see that the point that we found through calculus really is the minimum, which was the answer to the question. So if you really want to cut this in such a way to make the total area a minimum, you really would want x to be 16.596. The other piece, because it asks for both pieces, would just be 40 minus that. So 40 minus the 17.596. All right, so let's write down our two answers for part A. 22.404 and 17.596 centimeters. So this is a very real life problem where someone might actually give you a piece of wire 40 centimeters long and say, please make a circle and a square, but I want as little area as possible. I want to paint these shapes when you're done, or cover them with cellophane, but I don't have much cellophane. You know, please make it small. So this is what you want to do, 17.596. The next question is, how would you make your total area a maximum? Well, according to the extreme value theorem, this particular total area curve between 0 and 40 must have a minimum and a maximum. Okay? So we already found the minimum. Which one's the maximum? The 40, right? So I love how the question is asked, how do you make the total area maximum? The answer is you make x 40. But what does that mean for cutting? It means you don't cut. Instead, you take all your wire and you build a what? Square or circle?
Circle.
Circle. Remember, when x is 40, there's nothing left for the square. I love this question. So we see that if you really wanted to make as much area as possible, you would want to reserve all of the wire for the circle. That's what this is telling us. We want x to be 40, which pushes this point all the way over. When we lose the square, we keep the circle. Very cool problem. It shows us that critical points and endpoints are important. This has everything you need to know about optimization in this one problem. So the second question's answer is simply use all the wire to make a circle. Use all the wire to make a circle. And now you think back about your little SAT class or whatever you took. Maybe you took a class at Elite or something. Your teacher may have said something like, the circle with fixed parameter which has the maximum area is the circle. This is kind of proof of that statement. Okay. All right, let's go on to the next one here. I'll help you set up the equation. We don't have to solve it because there's nothing new to learn. Okay, this review session is really more about just reviewing the concepts, and then you can always take this problem home and see if you can figure it out. What was step 1 in optimization? Write a what? Write an equation. Now this is a minimum cost problem, so what equation will you write? write a cost equation, right? You will write a cost equation, make sure it's in one variable, and take its derivative set equal to 0, plug in endpoints, plug in critical points. This is a little hard to do. You have a cylindrical container. It has no top, but it has a bottom made out of maybe a thick metal, and then, of course, it has a lateral area, otherwise it wouldn't be half much of a cylinder, made of a different material. So these are different materials. And just think about all the cans you've held in your hand before, not a Coke can, but like a tuna can, right? The sides are a little more flimsy, you know, the top and the bottom are a little more sturdy. That's intentional. You can stack the cans even if the sides are a little flimsy, but you need the top and the bottom to be strong enough to withstand pressure when you put them in a crate, you know, like you stack tuna cans. So you definitely want to have probably a thicker, more expensive material for the top and bottom, and that matches this problem perfectly. So what we're saying is the sides are made of a cheap 5 cents per square inch sheet metal, and the material used for the bottom of that container is 15 cents per square inch, more expensive, heavier aluminum or whatever. Make sense? Okay, so you have to basically break this up into two shapes. That shell, of course, is just a rectangle, really. And the base of the can is really just a circle. Right? We did shell methods with integrals not too long ago, so you know that the area of this is 2 pi r h. And of course, it's a circle, so the area is pi r squared. And since there's no top, we only need one circle. But we don't really want an area equation. So you don't want to write your equation like this, 2 pi r h plus pi r squared. You don't want to write that. We want a cost equation, don't we? So we have to take the price of the sides material times the area of the side plus, and then the price of the bottom, 15 cents per square inch, times the bottom. You see, this is a cost equation. It is not in one variable. Not in one variable. That's a bummer. But there's one more clue in the paragraph. What did it say about the volume of the container? It says that the volume is 24 pi. They're trying to give you the volume, right? So this is your other clue. If the volume is 24 pi, then that means pi r squared h is 24 pi. In other words, r squared h is 24, which means r is either the square root of 24 over h, or you can think of h as 24 over r squared. Your choice. Pick one, substitute it into your cost equation. I hate square roots, so I think I would rather use the second one. And I will go over here and replace that h with a 24 over r squared and be done with it. I've got one variable. I'm ready for my derivative. Obviously, I should clean it up a little bit, right? So this problem proceeds by you finding the derivative, set it equal to 0, right? And then you'll do a cost analysis. Make sure you plug in the critical point or points, and make sure you plug in the logical endpoints. Now, what is my independent variable here? What's the variable? What's the variable? There's only one variable. What is it? R. What are the meaningful constraints on R? If you're designing a tuna can, you came to your boss and said, oh, I made a can with R equals 0. What would your boss say? You're fired. Right. On the other hand, if you're expecting to find a maximum possible value of R, that's not possible either. You can make your R as big as you want. You'll just have to sacrifice your height to keep that volume 24 pi. So basically, there are no meaningful constraints on R in this problem. It's not like a piece of wire. You're designing a can. You can make R as big as you want. And you can make the R as small as 0, I guess. But you're not going to have any volume at all, or surface area. So basically, you don't have to do endpoints on this problem, you see. just the critical point, and plug it back into the cost. Make sure it really is a cheapest cost, not a most expensive cost, you know. Okay, let's move on to related rates. So the first skill in related rates is you really need to know that we don't take derivatives with respect to x, we take derivatives with respect to time. So I think this might have been why people were confused a little bit with related rates. But what you need to do is you need to slap a ddt on both sides of these geometry formulas. See? So the left side is dAdt, the right side is pi times 2r times drdt. So if I ask you what's the derivative of pi r squared, you might be tempted to say 2 pi r, but remember, the chain rule is in effect, right? You need to take the derivative of r also, just in case it's changing. So basically it's 2 pi r, but it has a drdt. Okay? Let's try the second one. The left side is dv dt, and then the right side is pi times dr squared h dt. I could pull the pi out, right? Be careful with this one. It's a little more complicated, isn't it? Especially if radius and height are both changing. So you're going to have to treat this like a product rule. You've got an r squared and you've got an h, see? All right, so Brian, you want to help me with this derivative? It's going to be 4 things. I'm going to leave the pi outside. So 2r times...
sorry. 2r times h plus r squared times 1.
Okay, that's if you're doing derivative with respect to r's and h's. Technically, the derivative of r squared is not 2r. It's 2r times drdt.
Okay.
We have a new
drdt.
independent variable, and that's time. So 2r drdt times h. Rewrite that part, a little hard to read. So there's a pi right here. And it's 2r drdt times h plus r squared times what? Not 1, but 1 times dHdt, right. This is the correct derivative. Okay? In the same way, a squared, b squared, and c squared need to be treated with the chain rule. Next one's pretty easy. It's 2a dAdt equals 2, or plus 2b dB dt equals what, class? 2c dc dt. And there's nothing you can really do to simplify these. I guess you could cancel your 2's, but you really have 6 variables here. There's a, b, and c, which are the legs of a triangle, sides of a triangle. And then you have dAdt, dB dt, and dC dt, which are really the rates of change of the sides of the triangle. See? So there's kind of 6 things going on now instead of just 3. Before you panic, 5 of them are given. Or 4 of them are given, and 1 of them you get from Pythagorean theorem or something. But almost everything here is usually given, and they're asking for that 1/6 object. So there's like 6 things, but 5 are given. Okay, the next one is a little easier. The left side is dAdt. The right side is 2s what? ds dt. So we just have to be especially careful with the chain rule. This is probably area of a triangle, right? So there's a 1/2 here. But how do you take ddt of bh? And you have not been told that the base and height of the triangle are constant or anything. They might be changing. So what's the safest thing to do? Just use product rule again, right? So class, why don't you tell me what this is? What is it? dB dt times h plus dh dt times b. Again, 6 things going on. You have an area, you've got a rate of change of area, you've got base of a triangle, height of a triangle, rate of change of base of a triangle with respect to time, rate of change for the height with respect to time, but again, everything's given somewhere in the problem except one thing, you know. Okay, so now that we kind of reminded how to do the derivatives of both sides of these geometry formulas, let's go down and try
Right, this is short.
a problem. Yeah,
So if they say if like the height is constant, like it's not changing, then
then you're in
just
luck.
you just write h instead of dh dt.
No, you would assume that dh dt is officially 0. Its rate of change is none.
Oh,
So what happens is,
you'd still have
it
the
would be
same-
like, let's say dh dt was 0, it would be like you just pulled the h out in the beginning,
Okay.
okay? Because what's going to happen is this part's going to vanish.
Oh.
So it's just like pulling out the
That's-
h. But that would be a very special situation. It would have to actually say the height of the triangle is constant. But that does mean dh dt is 0. That's exactly what it means. Yeah, I'm glad you asked that. So this is if we had to pick one problem to do in our last 12 minutes, whatever, this would be it. The water in the cone problem, because it has every element of related rates in it, you know? It's a great problem. Okay, do you guys want to do this one, and then go home and try the free response problem from the 2002 test? Or do you want to do the 2002 free response one, and go home and try this made-up one?
Yeah, it's two.
Let's do the free response one, the real deal, the real AP test question? Sure. Okay. Okay, they were nice enough to draw us a picture, but that can also be a little misleading. I think every related rates problem deserves two pictures. One where things are specifically numbered, and one where things are changing. So I call them the general snapshot and the specific snapshot. They're giving us sort of a hybrid of these. So I'm going to draw my own pictures if you don't mind. My first one, I'll just trace over this, but basically saying that here we have a large cone with water in it. Okay? And when the water is in the cone, it takes the shape of a cone. So, of course, there's a smaller cone of water inside. Right? Now, what's not changing is the fact that this has a radius 5 centimeters and a height 10 centimeters. That's never going to change. This is the container. Right? What is going to change is the way the water looks. So the water has a radius r and a height h at all times. So how many variables do I have already? I have 2. Right? Okay, so keep that in mind. There's 2 variables. Besides volume of a cone, which obviously is something we need to work on here, can you think of any other geometric principles that show up in this problem? You see some triangles? I do too. You think Pythagorean theorem might help us here? Pythagorean theorem is interesting. It would help us find hypotenuse or something. Are we interested in hypotenuse? Probably not. Like, who really cares about the length of the edge of the water? You know, that's not important. But there's something else about right triangles, especially when you have more than one of them in a picture. Do you see 2 right triangles in this picture?
Yeah.
I do. How about now? See 2 right triangles now?
Yeah.
What's their relationship? Similar. They're similar. So before I forget, they already gave me this formula, but there's another geometric principle playing a part in this problem, and that is this. The height of the big cone that where the water is in, divided by the radius of the big cone that the water is in, should always equal the height of the little cone divided by the radius of the little cone. Do you agree that the ratio of h to r between large and small cones should be constant and should be 10/5? Okay, that is a really important statement because we don't have one equation, but 2 equations that we can take the derivative of. Okay, so the first one is given. This one was sort of implied in the problem. And we can write h equals 2r. Okay, any geometry formulas that you have recorded are going to get differentiated. Okay? You're going to be taking the DDT. Alright? So the first thing is, find the volume in the container. That is not a calculus problem. It says height is 5. So you're going to write V equals 1/3 pi, don't know the radius yet, r squared 5. But the radius, we have already figured out, is half the height. Right? That's what this means. The radius is half the height, or the height is twice the radius. So don't we know the height of the cone? I mean the radius of the cone? If the height is 5, and that represents 2r, if 5 is 2r, what's my radius? Not 10. The height is 2r. What's my radius? 5 halves, right? So the answer to the first question is 125 pi over 12. This is measured in cubic centimeters. Maybe this is their way of getting you to think good and early about similar triangles. Now, we already had h equals 2r, but the average student would be like, how am I going to figure out the radius? Then they would stumble across similar triangles. I'm suggesting you do it right up front. Okay, so you already had that relationship written down. I think that's why they created Part A, is to get the students thinking about similar triangles. That's kind of nice of them, steering our minds a bit. Let's go to Part B. Find the rate of change of the volume of the water in the container. Actually, this is kind of a best case scenario. You're actually looking for dV dt. That's what this means. Find the rate of change of volume. So you're looking for dV dt. I've seen much worse problems where they give you dV dt and ask for something else. Okay? Let's try to find the derivative of the volume formula. Okay? So I'm looking up here where my asterisks are, and I would like to find the derivative. Definitely going to be a 1/3 pi, just chilling out front. How am I going to take the derivative of r squared h? How do you take the derivative of r squared h? So what's the derivative of r squared h? What's the derivative of r squared? 2r dt. 2r dr dt, excuse me. Times the h plus, and now we need dh dt times r squared. So this is the same product slash chain rule we were doing back on the previous page, right? How many variables do I have now? Yeah, I've got r and dr dt. Those are different things, right? I've got h, I've got dh dt, I've got v and v dv dt, you know, v prime kind of thing. Okay. I don't have to isolate anything. I'm actually trying to find dv dt, so I just need to get this right side figured out. Let's plug in everything we know. It says the height is 5. Boy, that isn't much for a given, is it? Oh, man. That's it? Height is 5? But wait a minute. If the height is 5, we already figured out earlier that the radius is what? 2.5. Or I'm going to put 5 halves. So let's stick in that for any r's we see. So this is 5 halves. This is 25 fourths. dr dt, dh dt. 2 more unknowns, no more givens. Look back at the original problem. There's a given we glossed right over. We didn't read it. Wasn't there one more given right here? H is changing at the constant rate. -3/10. What's that? What are they giving us? That's dh dt. Yeah, so that's given. Beautiful. Stick it in right here. I have no idea what just happened. My computer's saying, I'm done this week. Can you please give me a break? No, work harder. I is your slave driver. There it is. Okay? Oh man, what about dr dt? Well, remember I told you that any geometric formulas we wrote down, we need to differentiate. We never took the derivative of that. That's our last clue. So if you take the derivative, that's really easy. What's the derivative left side? dH dt equals 2 times dr dt. That's the last clue in this problem. So there's one more little factoid we never wrote down, that dH dt is 2 dr dt, you see. And if dH dt is negative 3/10, then we have negative 3/10 is 2 dr dt. And this means, if you divide both sides by 2, that dr dt is negative 3/20. It's just half of dH dt. Now that's a lot of work, and this is an A-B problem. Like, it's not BC Calc, it's A-B. It'll show up on both tests, actually. Maybe the BC test will have like a fourth question or something, but this just needs to be cleaned up and simplified, and don't forget the units. They always ask for units. Indicate units measured, and they're very mean about it if you forget them. So let's just think about the units. It's volume and time, dV, dt. So what would be good units? We can slap them on right now. What are they? Volume is cubic centimeters, hours for time. So make sure that you have that in your answer. I'm running out of time to simplify it, okay? So this is like worst case scenario, the double cone. The volume formula is ugly, similar triangles is involved. Most problems are a lot easier than this, okay? So that's why I use it as an example. The only thing that can make it worse is if they give you dV dt and ask you for dH dt, which I did on my test. So you can actually go back and look. I gave you the worst possible scenario on every test this year. I've made this year so hard, okay?
Thank you.
I'm trying to make it easier for you when you take the actual AP test. That's what correction space is all about, okay? There's one more problem on here. They always do this. They throw in one critical thinking problem, okay? Show that the rate of change of the water in the container due to evaporation is directly proportional to the exposed surface area of the water. Wow. Okay, first of all, I taught you how to read this earlier in the year. Rate of change of volume. What's that? Derivative of what? Volume. That's dV dt. Is proportional to. I taught you how to write that. Equals, that's your is. How do you write proportional to? K times. This is pronounced. Is proportional to. Is proportional to. Equals K times the exposed surface of the water. Now, if you're holding one of those nifty little cups, Elite has these cups. Anyone go to Elite? They have these little cups of water. They're like little cones. That's all they have. They're tiny little cups of water. Everything else about Elite is awesome. Okay? Really awesome. I love Elite. But what is the exposed surface of the water? It's just the top circle, right? Yeah. So all you're trying to do is this. Find K. So if you know how to read these problems, you are way above the nation. Okay? Because most of the people will spend their time trying to read this, and they're like, whatever, and move on. They don't have that much time. They don't have time to interpret it. You've learned already how to interpret it. So dV dt is K times pi r squared. What is K? That's what it's asking. So demystify the problem, first of all. We already wrote down dV dt, didn't we? In fact, it's right up above there. It sounds like they want the more generic version because we need to have an r squared in it, right? So I'm going to write dV dt equals 1/3 pi times r squared. It was actually 2r dr dth, remember? 2r dr dth plus r squared dh dt. Somehow I got to pull a pi r squared out. And I actually want to put the I want to put that 1/3 back inside, okay? I want to get that 1/3 back inside. All I want on the outside is a pi and an r squared. Understand? I want a pi r squared there. So I can steal the r's and bring them out. Remember, h is 2r. Remember that? Let's replace that with 2r and a split. Okay? This way we'll have a pi r squared in every term. I'm absolutely exhausted, so. This is a 2r we learned earlier. Alrighty. I wanted a pi r squared out front. We can achieve that. Let's steal all the r's and put them outside. Pi r squared over 3. Inside I now have a 4 dr dt and just a lonely little dh dt I stole is r squared. Everyone see what I did? I stole all the r's from the inside. And I really didn't want that 3 out front. Let's put that back inside. Let's just leave the pi r squared chilling out front. Here we have it. 4/3 dr dt plus dh dt. We done did it. We showed that the rate of change of the volume is proportional to the exposed surface. We did it. We showed that pi r squared is involved somehow in the evaporation.
Would you have to distribute the
I probably made
one-third
mistakes
to
there.
the DHDT?
Yeah, I did a 1/3 on that guy too. Thank you. I got so excited about what we've achieved. You know what we just proved? We proved that the evaporation of water in a cone is really dependent on what's exposed. It makes sense, right? It's not about how deep the water is. It's about how much is exposed to the surface, the molecules escaping the surface water, the surface tension of water, right? That's what we proved. That's the physical phenomenon. Now we just need to find this number. I thought dHdt was 3/10, -3/10, and I think that was -3/20, right? We already have dHdt and dRdt. Put them in.
Where do you need it?
Remember dHdt was twice dRdt.
Oh, yeah.
So we're going to put in -3/10 for dHdt and -3/20 for dRdt, and we should get that constant of proportionality. Danica and you need the pi r squared out front because they said show that the rate of change of volume is directly proportional to pi r squared. So we need the pi r squared outside.
Well, because dV equals that, so would you divide that pi r squared on both sides?
Don't they like cancel out?
Yeah, they cancel.
Wasn't that the point of getting the pi r squared?
That'll give you k. We're trying to show that the rate of change of volume has a pi r squared in the formula. That's what they're asking for. That's the next question. There's 2 questions in this problem. First they ask you to show that dV dt contains a pi r squared. They want us to show that dV dt has a pi r squared in it, and it does. Then they want us to find that number that you multiply pi r squared by to get dV dt. So now we need to get this number, that's k, plug in -3/10, plug in -3/20, done. 9 out of 9. Wouldn't that be awesome? I think you could do this. I really do. You guys can get 9 points on that problem. I know you can. Especially if this is sort of worst case scenario for related rates. Every question since 1969, every single free response question has been released. You can find a packet of them online. There's PDFs. I don't mail it around because they also try to sell it. And I'm not trying to steal their money, but I've heard that even their own website, even the College Board has posted for free. So if you can find it, great. If you just want me to print a bunch of free responses for you, I'll do that. Okay? Probably won't give you my 2013 ones or something, but that's just because I'm saving them for practice tests. But you can find those online too.